suitable for if you have a situation where you have two decision variables only, right? If you have more, then you have to use other methods. And the methods that we have talked about, I think last lecture, is the simplex methods. And basically, simplex method utilize a simplex algorithm, which can be used in order to define the optimum conditions or optimum value of the decision variables for a given situation. And we've gone through, I think, maybe two examples on how to do that, and you can see it's quite tedious. It's iterative process where you have to use Gauss-Jordan rules or algorithm to solve the iteration problem. And the topic that we have covered for the simplex method last lecture is for a situation where all the constraints are basically less than or equals to a particular value. And in order to do that, then basically you have to use slack variables, right? S. Towards the end of yesterday's lecture, we started to talk about the big M methods, and the big M methods is utilized for you to perform simplex algorithm to solve a linear programming problem whenever you have the utilizations of artificial variables, right? So whenever you have a situation where you have to utilize artificial variables, then you have to use one of the methods that you can solve linear programming using simplex method is the big M methods, right? The situations that require you to use artificial variables is when your constraint is equal to a value or greater than or equals to a value. Only on those situations. So if you have those situations, then you have to use artificial variable. And if you have artificial variable, then you need to use one of the methods that can be used to solve it is basically using big M methods, right? And so that's where we stop last lecture. So again, any questions with regards to those topics that we have covered? If not, I'm just going to proceed with our lecture on big M methods. No? All right. Okay, I'm sharing lecture materials right now. Can you see the I think this is the big M methods notes on the screen?
Yes, we can.
All right. Okay, so just a recap on the big M methods. As I mentioned just now, this is the big M methods is utilized whenever you have linear programming with greater than or equals to constraint. Right, so whenever you have this, then basically you're going to use artificial variable to solve the problem. And whenever you do this, and one of the method that you can use is the big M methods, right? Okay, I think we have covered this. We have covered this, and we covered up to here, I think. So one of the important things that you need to understand and remember, whenever you have these big M methods, if the linear programming is a maximization problem, meaning that the objective function is to maximize something, right? Then you need to add minus m value multiplier to the artificial variables. And for this particular case, as mentioned earlier, so this is the artificial variables. In the examples before, we use a, right? So it doesn't matter what variables you want to use, r or a, as long as you define it upfront. Okay. So, and if the linear programming is minimization problem, then the multiplier for the artificial variables in the objective function would be plus m, plus m. And the reason being is basically, as I think explained last lecture, you want to force the artificial variable not to be part of the solution. So whenever you have maximization problem, if you have a multiplier of minus m, meaning that if you add that particular artificial variable in the solutions, it will give a very huge negative number. So by default, the simplex algorithm will force that artificial variables to be not to be one of the not be one of the solution. So similarly for the minimization problem, you put plus m, meaning that is a huge plus m number, meaning that if you include artificial variable as part of the solutions of the minimization problem, then that the value of m will be very, very huge. So again, the simplex algorithm will force the artificial variable not to be one of the solution. Okay. Okay, so now let's look at in detail on how to execute these big M methods. So also, I think I explained yesterday, if all the artificial variables are equals to 0 in the optimal solution, then we have found the optimal solution to the original problem. But if any artificial variables are positive in the optimal solutions, then the original problem is infeasible. So what this means is this. What this means is this. At the last iteration of your simplex tableau, you say, for example, this is you have. I just want to make sure that you understand this. Let's say this is x1, x2, and then this is let's say, for example, a1. To make things simple, for example. And at the end of the iterations, you have x1 and x2 as a solution, meaning that maybe you only have two constraint only, right? Then and the value in here, let's say, for example, you have 5, you have 3. And this z value, let's say, for example, 10. This is whatever value lah. So how you interpret this table is basically the solution of this problem is basically x1 equals to 5, x2 equals to 3, and z is equals to 10, right? And what is the value for a1? A value for a1 is basically 0 because it's not part of the solution. If this is your result, then basically you are saying that the artificial variables are equals to 0 in the optimal solution. If this is the case, then basically you say that you found the optimal solution. However, if the final iterations of your simplex tableau looks like this, A1 like that, then the solution for this is basically like so, right? And then this is x2. So the way to read this, then basically you're saying that x1 is 5, a1 is 3. So a1 is part of the solution, and z is equals to 10, and x2 is equals to 0. If this is the result that you get at the end of the simplex tableau calculations, then you're saying that the artificial variables are positive because the value of it is 3 in the optimal solutions, and the original problem is infeasible, meaning that the problem the linear programming model that you got cannot be solved. Right? So this is what it meant. So whenever you see the optimized solution, it looks like this, where A1, which is artificial variable, has a value. It indicates that that particular linear programming problem, linear programming model cannot be solved, cannot be optimized. Hmm? Understand? All right. So let's look at how to execute these big M methods. Big M methods. We are going to use these particular examples. So these examples is basically z is equal to 4x1 plus x2. So there are two decision variables, x1 and x2. And the objective function is minimization. Minimize z equals to 4x1 plus x2, subjected to the constraint. And there are three constraints altogether. There are three constraints, the first, second, and third constraint. And you have to convert this to simplex algorithm, right? And in order to do that, then basically, again, we have gone through this. We have to use slack and surplus variables. And since since if you look at this particular constraint, so if you convert this into simplex variable, then this become uh, 3x1 plus x2 plus what? Anybody? If this is 3x1 plus x2 equals to 3, so this is the linear programming model. You have to solve it using simplex, right? So then you have to convert the constraint into simplex equation. So in order for me to do that, then the first constraint, which is 3x1 plus x2 equals to 3, become what? 3x1 plus x2 plus, if it's plus what?
A1.
Please L plus A1 equals to 3, right? The second constraint is 4x1 plus 3x2 plus what?
Plus one.
Plus what?
S1.
S1
S, S1
plus
plus
equal to 6.
A A
A2.
equals to 6.
Is it correct?
No.
Is it correct?
Uh,
What?
Right.
And anything wrong with this equation?
Oh, minus S1.
Yes. So this should be
Minus S1.
minus S1,
Uh,
right? And the last one should be x1 plus 2x2, what? Plus what?
A1.
No,
Eh,
plus S2,
S.
right? Equals to 4, because this is less than or equals to, right? So if it's equals to, then you have plus artificial variable. If it's greater than or equals to, then basically this will be minus S plus artificial variable. If it's less than equals to, then what you have to do is plus n S, which is the slack variables, right? Okay, so then the first thing you need to do is convert this, right? Convert this. Okay. Okay, so that's what's being shown in here. So it's being converted as such, right? And the other thing that we need to do to this is to rewrite the z value, right? So now z is minimize z equals to 4x1 plus x2. If you want to include the s, plus 0s1 plus 0s2, right? Plus R1 or A1 plus R2. And the multiplier for the R1 and R2 adalah big M. And since this is minimization problem, right? You put plus M, right? R1 plus M, R2. If this is maximization problem, then Z would be 4x1 plus x2 plus 0s1 plus 0s2 minus M R1 minus M R2. You get it? So if it's minimization, then you rewrite the objective functions such that it has a big M multiplier for R1 and R2, which is positive. And if it's maximization, then you have to put a big M multiplier for the artificial variable, but it must be minus M R minus M R1 and minus M R2. Is that okay? Any question? All right. Okay, now once we have these equations as such, then basically we come up with the initial tableau. So the initial tableau is just what we did last time, the same, where you have in the on the first row, basically you have x1, x2, s2. For this particular case, in the book, it wrote here s2 and s3. Doesn't matter as long as you are consistent. And they put s2 and s3 apart like this. It doesn't matter as long as you are consistent. Okay. And then R1 and R2, which is artificial variable 1, artificial variable 2. So so this is the top of the top row of the tableau, and then the solution. And then for each of the constraint over here, you have 3 constraint. 1, 2, 3. So because you have 3 constraint, then you have 3 initial basic variables, which is R1, R2, and S3. Right? The question, why S2 is not part of the basic solution, initial basic solution? Why we choose for this particular uh, for this particular uh, uh, constraint? Why do you use R2 as the basic solution rather than S2? Anybody? So I think I explained this earlier. The reason being, if we put S2 as a basic solution in here, right? Then if we set x1, x2, and R2 equals to 0, then S2 minus S2 is equals to 6. So S2 equals to minus 6. So it will not obey this requirement, right? So that's why we need to introduce artificial variables, and the initial solution for the initial tableau for whenever you have at minus s2 plus r would be r2, which is artificial variables, right? Okay, does that make sense? All right. And also remember, the number of initial solution in the tableau, right, will always be the same as the number of a constraint. Let's say if you have 5 constraint in here, then you're going to have 5 basic solution in here, initial 5 basic solutions, right? It's always follow the number of constraint. Okay. Okay, let's look at this particular. So then basically you can transform this into this initial tableau. So let's look at this initial tableau. So so when you use big M methods and you set up a tableau as such, right? This tableau has a problem actually, right? So now if we substitute, so if you look at this, what this indicates is the solution is basically R1 is equals to 3, R2 is equals to 6, S3 is equals to 4, and Z is equals to 0. Right? So let's put a Z here. Right? That's what this says lah. So if you have what this means, if you have objective functions Z, and the objective function for this particular case is equals to 4x1 plus x2. 4x1 plus x2 plus m r1 plus m r2, right? So since x1 and x2 is not x1, x2, and s2 is not part of the solution, x1 is equals to 0, x2 is equals to 0, s2 is equals to 0. So if I substitute value to calculate z, then what I got is 4 times 0 plus 0 plus m times r1 is equals to 3 plus m R2 is equals to 6. So this is 9m, right? But the value of z here is 0. So it does not tally. It does not tally. So because of that, there's inconsistency in the tableau. And we need to address that inconsistency. Right? So it says here, if we substitute 3 and 6, which is R1 and R2, into the objective function for R1 and R2, respectively, then basically we have Z is equals to 3m plus 6m equal to 9m. This is what we got. In our tableau, however, Z is shown to be equals to 0, right? So we can eliminate this inconsistency by substituting out R1 and R2 in the Z0. In the Z row. So first you need to multiply each of the first two constraint rows by m and adding them both to the current zero. Okay. So what this says is this. So because of this, there's inconsistency in this tableau. So we need to fix it. So how do we fix it? Okay. So whenever you have this situation, usually, most often than not, unless there's a very, very, very minor occurrence, what happened is, if you look at this, this is the basic variables, R1, R2, R3, S3, right? In most cases, in almost 90%, 99.9% of the case, if you have a basic solution variable in here, R1, R2, R3, the Z value for that particular variable should be 0. So for example, this R1, right, which is one of the basic part of the basic solution for this particular tableau, the Z value is minus m, not 0. This R2 is minus m, not 0. S3 is 0. So we have to make sure that the multiplier for the Z for the R1 and R2 here become 0. Okay. So we can look at, let's say, for example, the examples that we did yesterday. Can you see this presentation? The lecture 2 notes? Boleh nampak tak?
Boleh.
Alright. So kalau we tengok ni, the variable, this is a tableau for examples that we did yesterday. So the basic variables for this particular case is S1, S2, S3, S4. So this is S1, S2, S3, S4. If you look at the Z value for S1, S2, S3, S4 are 0, 0, 0, 0. Right? So no problem. Then if you substitute all this value into the objective function, then basically you should be able to get a 0. Right? But it's not the case when you use this big M. Right? When you use this big M, that's not the case. For when you use a big M to solve the problem which has artificial variables. So we need to address this first, right? So in order to address this, then we need to zero out M1, this minus M and this minus M for R1 and R2 of the Z. The way to do it is this. Okay, we need to multiply each of the first two constraint row by M and adding them both in the current Z row. So to illustrate this, this is basically what's being done now. So we need to define a new Z row such that the multiplier of the Z for the R1 and R2 is 0, right? So this should be 0 and this should be 0, right? So to do that, basically what we can do, we can multiply this row R1 with an M and R2 is an M. If we do that, then basically then the value for R1 row become 3M, 1M, 0M, 1M, so on and so forth. And then we can add them up. When we add them up, then this value of M will become 0. So let's do that. Let's do that examples, and then hopefully it will be clear to you, right? So this is the methods on how.
Anh nghĩ là what là gì?
Okay. So this is the rules that you should remember on how to do it. But the objective is to make sure that this minus M value is 0 and 0. Right? Multiplier for the Z for the R1 and R2. So the new 0. So you need to replace this Z row with a new Z row. So how to do that? Basically, you have all 0, which is minus 4, 1, 0, minus M, 0, and 0, right? Equals to the old row, which is the old row, this, plus M times R1 row. So if you look at R1 row, is this. So this row now become 3M, M, 0, M, 0, 0, and 3, 3M. So you multiply this whole row with an M, right? Plus M times R2 row. So this is, where's R2 row? This is R2 row. So you multiply M with all the multiplier for that particular row. Then you have 4M, 3M minus M, 0, M, 0, and 6M. And then the next step is you add them all up. So you can get a new 0. So if you add them up, then basically you have a 3M plus 4M minus 4. You have 7M minus 4. Over here you have 4M minus 1. This is M, 0, 0, 0, M. So remember, this is X1. This is X2. This is S2, this is R1, this is R2, this is S3. This is the solution. So if you look at this, if you look at this, then R1 and R2 become 0 now, right? Any questions on this? All right. So remember, these are equations, and we are solving it. We are solving the equations like a simultaneous equation using linear programming methods. So you can use these operations because then it will change zero based on the change on the R1 row and R2 row, right? So relatively they are the same. It's just that you want to make sure this R1 and R2 multiply for Z become 0, right? Then next step, basically you take this new Z row and then substitute it into the tableau, uh, to initial tableau. So now our tableau become this. So from here to here, no change. The only change is this. So this is the Z. So this is the new Z row. How do we get this? Using the operations that we did just now. Right? This operation, which is new 0 is equals to all Z row plus MR1 row plus MR2 R2 row. Right? Now, once we substitute the new 0 in here, then we can do double check where we have over here R1 is equals to 3, R2 is equals to 6, S3 is equals to 4. And if you substitute this in the objective function, and basically you're going to get, so objective functions is Z equals to 4x1 plus x2 plus m r1 plus m r2, right? So if you substitute this, then this is become 4 times 0 plus 0 plus m is equals m r1 is equals to 3m plus 6m, you have 9m. So now you are consistent. The tableau is consistent, right? Any questions? Okay. Boleh? Actually, I'm worried bila tak ada orang response. Not sure whether anybody following the lecture or not. Is it okay? Or any questions?
Okay,
Okay. All right. So basically, once we got that tableau, then what you do is solve this tableau. Solve this using the simplex methods that we did last time. All right, similar methods. So basically, there'll be iteration process, and you should solve it once you solve it. Basically, so this is minimization, right? So minimizations, then basically you want to look at the value whether it's optimum or not. If it's not optimum, then you identify what is the entering variables, right? Once you define the entering variables, then you need to define the leaving variables, right? And then you substitute them, and then you use Gauss-Jordan rules to substitute all the rows, right? And then you solve it that way, right? So if you do that, then basically the next tableau looks like this, and finally this is the optimal solution that you should get. Yeah, this is the optimal solution that you should get. Okay, so what I want everybody to do. So this is our tableau, initial tableau, right? And what I want you to do is solve this. Okay? Attempt to solve it now. Faham tak? Hello?
Tak faham lah tu.
Tak faham apa yang tak faham?
Nak solve.
Macam mana nak solve this?
Ah,
Okay. All right. So let's do that together, step by step. But there are a lot of calculations, and we're going to what are these is so let's do it together. But let's do it together. Let's do it together. Hopefully, I'll go through once, and then see whether you can pick up or not. Huh? So again, this is a problem. Can you see this? A new page. Boleh nampak? I just changed the file. Can you see this?
Boleh nampak.
Boleh. So this is the situation that we have. So this is the linear programming model that we have to solve, right? And basically we convert all the what do you call it? The constraint into simplex algorithm, right? So we have 3x1 plus x2 plus a1 equals to 3. And then 4x1 plus 3x2 minus s1 plus a2 equals to 6. And then the last one is x1 plus 2x2 plus s2 equals to 4. And then you rewrite the objective functions. So since it's minimizations and it has artificial variables inside it, so the multiplier for the artificial variable should be plus, not minus, right? And if I rewrite it, it becomes 4x1 plus x2 plus 0s1 plus 0s2 plus ma1 plus ma2, right? So I think this at this point, I think should be clear for you guys, right? Then basically you set a new tableau. Set a new tableau. So I work it out on my own so that I won't waste much time doing it. But we can go through it, and if you have questions, then let me know. Okay? So the tableau become x1, x2, s1, s2, a1, a2, and solution. So we just plug in the number, and when you plug in the number, as we discussed just now, I explained just now, if I substitute a1 equals to 3, a2 equals to 6, s2 equals to 4, the z value should be 0, right? But when I did that substitutions, the z value is 9m, right? Not 0. So there's inconsistency. So because of that, then we need to solve that inconsistency. How to solve it? Basically, remember the new row of z equals to old 0, right? So old 0 is minus 4, 1, 0, 0, minus m, and 0. So this is all 0. Minus 4, minus 1, 0, 0, minus m, and 0. And m times r row. So r is basically artificial variable 1, which is a1, right? So m times a1 equals to 3m, m0, 0, m0, 3m. And accordingly, for the a2 row, become 4m, 3m minus m, 0, 0, m, 6m. And you add them up together. So new row is you add up m1 row plus m2 row and all z row. Then what you got is basically this value, 4m minus 7m minus 4, 4m minus 1 minus m0, 0, 9m. Right? At this point, any questions? No? Okay, so next step is basically we're going to substitute this new row into here. right? So this new zero, we're going to substitute into here, and that become our initial tableau. So if we do that, this is what we got. The first initial tableau, right? Where I have new zero in here. Okay. Any questions at this point? No? So what's the next step? So now we have this tableau, right? Initial tableau, and we want to solve it. What's the next step?
Find the most negative.
Fine. So if it's maximization, right? So let's look at okay. So if you look, can you see this this note that we went through during simplex methods? Nampak tak? Yang saya bulatkan ni. Nampak tak?
Yes, yes.
Okay. I mean, you have first thing you have to check whether the solution is optimum or not. Macam mana nak check optimum, whether the solution is optimum or not? For maximization, right? The all zero multiplier is non-negative. And so kalau maximization, if the objective function is maximize something, if all the zero multiplier is non-negative, semua positive, then you say it's optimum, that you are done. Right? But for minimization, all zero multiplier are non-positive. Maknanya all the multiplier are negative ataupun zero. If that's the case, then you achieve optimum conditions and you can stop. Yeah. So let's look at our examples. This, right? So let's look at this one. Z value. So 7m minus 4, is this positive or negative? Seven m minus 4, is it positive or negative?
Positive.
Why positive? The question is why positive?
M larger than 0.
M larger than 0. So what is m? We define that the m. M is a very, very huge number, right? How huge? Very huge, right? So 7m minus 4, of course, is going to be positive, right? Because m is very huge number. So 7m minus 4 must be positive, right? Does it make sense? Does it make sense? So m
Yes.
as minus is, that's why we call it big M. M is very, very huge number. How huge is huge? You can put, let's say, trillion relative to other variables, maybe trillion, for example, you know. So 7 times m equals to 1 trillion. So 7 trillion minus 4, of course, can be positive, right? So for m minus 1 is also positive. Minus m is negative, 0, 0, 0, 9m positive. So if you look at the multiplier for the z, right? For the z, remember our condition just now? If it's minimization, eh, all zero multiplier are non-positive, meaning that is zero atau or negative. But we still have positive multiplier here, right? This is positive, x1 multiplier positive, x2 is positive. So because of that, then this is not optimum yet, right? So this solution, the first tableau, I put here number 1, is not optimum yet. It's not optimum yet. So if it's not optimum, because you still have positive value, what do? Then, if not optimum, then select the entering variables as the non-basic variables. So which one you should select? For maximization, the most negative objective coefficient. For minimization, the most positive. So beza kan, during apa ni examples that we gone through in the simplex method previously, is maximization. So you choose the most negative number. But for minimization, then you choose the most positive number, the other way around. Right? So if you look at this, 7m minus 1, 4m minus 1. So these are the two positive. Which one is larger? Which one is more positive?
4m minus
7m
1.
Yeah, 7m minus.
minus
So
4.
this become the entering variables now, right? And what's the leaving variables? Then we have to calculate the ratio. Same step that we did last time. So this is 3 divided by 3, 1. 6 divided by 4, 6 over 4. 4 divided by 1, 4. So the smallest value adalah 1. So because of that, A1 will be leaving, X1 will be entering. So next iteration, then A1 is no longer there and we substitute it with a X1. Right? Any question? Okay. So then we use the same methods that we did before. So this is X1. So in order to get this row, then you divide the old row's number with a pivot number, which is 3, right? So this become new pivot row, right? So then basically you divide everything here by 3. So 3 divided by 3 is 1. 1 divided by 3 is over 1 over 3, 0, 0, 1 over 3, 0, and 3 divided by 3 is equals to 1. Right? And then for the rest, then basically you use these rules for all other rows, including Z. You use these Gauss-Jordan rules, right? So basically, a current, for example, for this one, a current row, which is 4, right? Minus its pivot column number, which is 4, times the new pivot row number, which is 1. So basically, it becomes 0. Lah. 4 minus 4 times 1 becomes 0. You do the same thing for all this value in here. Okay? Any questions? That's why I want you to attempt doing it on your own. I can give you, let's say, for example, 10 minutes to do this, so that you have some, you know, at least you explore how to do this on your own. But if you don't want to do that, it's fine. We can just go through this verbally like this, because if you have to do it one by one, it's very time consuming. Huh? Okay, so S2, the same thing. You use these Gauss-Jordan rules. So this is 0, 5 over 3, 0, 1, minus 1, 3, 0, so on and so forth, right? What I want to go through a bit detail is this Z value, right? So for this Z, right? So you use the same approach. So for this one, right? So let's look at this Z. So for this value, then what I do is the old value, which is 7m minus 4, right? Minus the pivot number, right? Its pivot column coefficient, which is 7m minus 4 also minus 7m minus 4, right? Times new pivot row. In this particular case, the new pivot row is equals to 1. Okay? So times 1. So then basically you have 7m minus 4 minus 7m minus 4, you have a 0. That's why you have a 0 here. Okay, next. I want to go through this because there's a calculation with regards to that involve m, so that you know how it's being done. Next. So for this value, so again, the old 0 is equals to 4m minus 1 minus what? Minus 7m minus 4, which is the pivot column coefficient, times the new pivot row number, which is 1/3, right? Times 1/3. So what I got here is 4m minus 1, right? Minus 7m minus 4/3, right? So if I want to do everything over 3, then what I got is 12m minus 3. I open up this bracket, minus 7m plus 4, and everything here over 3. Then 12m minus 7m is equals to 5m, and minus 3 plus 4 equals to plus 1/3. So that's how I got 5m plus 1/3. Is that okay? Any questions? No? No questions? Okay. No questions, and we move on. So then basically you do the same thing for the rest. So if you do that, become minus m 0, 4 minus 7 minus 7m/3, and this is what you'll get. So again, then again you look at this, and then basically you want to look at this, and you want to check for the optimality conditions, whether this is optimum or not, right? So is this optimum? This solution, is it optimum?
No,
Anybody? Why not optimum?
still have positive value.
Yeah, still have positive value. Still have positive value, because this minimization, right? So whenever, if minimizations, if you have all negative value or 0, then you're optimum, right? So we still have positive value in here. So 5m plus 1/3 is positive, minus m is negative. How about this one? 4 minus 7m/3, is it positive or negative?
Negative.
Negative, right? Because m is a very huge number.
Huge.
Yeah, so because of that, then this particular column, x2 column, is the pivot column, and x2 will be entering the variables as a basic variables, and x2 will be entering, and watch which one will be leaving. Then we do that ratio calculation again. 1 over 1 over 3 equals to 3. 2 over 5 over 3 becomes 6 over 5. 3 over 5 over 3 becomes 9 over 5. And the smallest value is this. This is the smallest. So because of that, A2 will be leaving and X2 will be entering. So next iteration, we have X1, X2, S1, and Z. Right? So we perform a similar Gauss-Jordan rules operation again, as shown in here. And this is what we got. Right? So at this particular junction, then if you look at the Z value, you have a 0, 0, 1 over 5, 0, 8 over 5 minus m, minus 1 over 5, right? So we still have one positive value in here, meaning that the solution is not optimum just yet, right? So this will be again selected as a pivot row, pivot column, which is S1. So S1 will be entering the solution. Which one will be leaving? Then we have performed the ratio calculations. So 5 over 3 divided by 1 over 5 is equal to 3. 6 over 5 divided by minus 3 over 5 is negative 2. So we can ignore it because we look at the positive number only. And 1 over 1 is equals to 1. So the smallest ratio is this. So we know that S2 will be leaving, right? And S1 will be entering the solution. And next iteration, we have X1, X2, and S1. And we perform similar operation, Gauss-Jordan operation again. And basically, this is the solutions that we got. Z equals to 0, 0, 0. S2 is minus 5. And A1 is 7 over 5 minus M. And A2 is minus M. So this indicates that the optimum solution has been achieved because all the value of Z multiplier is negative or 0. They are negative or 0. So this is the solution. So what's the solution? Solution is basically x1 equals to 2 over 5. X1 equals to 2 over 5. X2 is equals to 9 over 5. And S1 is equals to 1. And if you plug in into the objective functions calculation Z, right? What you got is 17 over 5. Any questions? And in this solution, if you look at it, x1, x2, s1, so a1 and a2 is not part of the solution. If a1 is still part of the solution in here, meaning that that particular problem, linear programming problem, is not solvable. It's not solvable. Right? And again, I want to remind you, on checking, making sure that your calculation is correct. Make sure if you have basic variables like this, A1, A2, and S2. If you look at the multiplier for those A1, A2, and S2, you have 2, 0. You have only one. You have only one row with a value of 1 and the rest are 0. 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0. Right? If it's not, let's say, for example, you have a 1, 1, 1, 1, 1, or 1, 0, 1, something wrong with your calculation. Similarly, if you look at this, the basic variables is x1, a2, s2. So if you look at that particular row, so x1, we have 1, 0, 0, right? And then z also 0 value. A2, if you look at A2, is 1, 0, 1, 0, and z is equals to 0 also. And S2 is 0, 0, 1, 0. Right? If not, if let's say, for example, you have 1, 0, 1 again, something wrong with the calculation. This is how to check it. To check your calculations. Right? The other thing is at the end of it, if you got this, then basically the solution is as such, z equals 17/5. What you can do, you can look at the objective function again and substitute x1 and x2 to the objective functions. If the calculation here using the objective function is not the same as 17/5, something wrong with your calculation. So there are many ways for you to check whether the calculation that you did during the iteration process is correct or not. Okay. Any question? No? All right. Okay, so let's go back to the slide. So as mentioned earlier, I show you that we went through the calculations, and this is the result. So we got the same results. So basically, these are the solutions, and all other variables equals to 0. Since the artificial variables equals to 0, then basically you're okay, right? And this is the optimum solution. Okay. Remember, the use of penalty M may not always force the artificial variables to 0 levels by the final iteration, right? This can occur in case where the given linear programming has no feasible solution. So as mentioned just now, whenever you use this penalty big M, right? uh, the artificial variables is not always go to 0 level at the final iterations. So if this is the case, then what you do is you have to declare that the linear programming has no feasible solution, right? If any artificial variables is positive in the final iterations, then linear programming has no feasible solution space. That's what it meant. Okay. Theoretically, the applications of big M techniques, requires that M approaches infinity, meaning that we assume that M is huge, approaching infinity. But whenever you do computerize the solutions algorithm, M must be finite while being sufficiently large. So whenever you want to do programming, let's say you want to do programming to solve using big M methods, you still have to assign M, this M, to a particular value, and you can assign it to a huge value, sufficiently large, right? But when you do that, there is possibility there is a pitfall. There's a pitfall in this case. However, that if M is too large, it can lead to substantial round of error yielding an incorrect optimal solution. So when you do this, when you do programming, you assume M as a number. If it's too large, then basically you can have a substantial round of error. Right? For this reason, most commercial linear programming solver do not apply M methods, but use rather than artificial variable methods called two-phase method. So the other methods that can be used to solve the linear programming problem whenever there exist the artificial variables in the constraint is to use two-phase method. Right? And most of the commercial linear programming solver, including the Excel solver, use two-phase methods, right? And that's our next topic, right? To talk about, to see how this two-phase method is being conducted, right? Any question? All right. If no question, then basically that's the end of the big M methods. And I'm going to move on to the two-phase methods. All right. In the two-phase methods, do you guys want a break? Or you guys is on the break already? Okay, let's move on. So let's look at the two-phase methods. The M methods, the use of penalty M can result in a runoff error, as explained just now. The two-phase method alleviate this difficulty by eliminating the constant M together. So in the two-phase method, we do not use a big M. We don't use this M multiplier, right? And it consists of two phases. And the two phases, basically, these two phases, the first phase attempts to find starting basic feasible solution, right? So the first phase, what it does is basically find the basic feasible solution, right? And phase two, solve the original problem. Okay? So again, I mentioned the two-phase methods is the preferred methods whenever you use programming because of the runoff error that might occur using the big M methods. So most of the software being designed using these two-phase methods. And in the two-phase methods, there are two steps. The first step is to attempt to find the starting basic feasible solution. And the second one is solve the original problem. And we're going to go through those two methods using the same examples that we did when we discussed about big M methods. Huh? Okay. Phase one. So what do we do in the phase one? So in the phase one, this is a phase where we try to define what is a starting solution, the basic starting solution. Right? So phase one, what you do is put the problem in equation form and add the necessary artificial variables to the constraint to get starting feasible basic solution. So this is basically what we did. So this is what we have been discussed for. If the constraint is equals to, then you add artificial variable. If it less than equals, you add slack variables. Right. If it's greater than equals to, then you put surplus variables plus artificial variables. So this is first thing that you need to do. Okay. Secondly, set new objective functions such that it minimizes the sum of artificial variables. So the second step is completely different than what you used to. Because whenever you have linear program problem, it has its own objective functions, right? But in the phase one of the two-phase method, you have to create a new objective functions. What's the objective functions? New objective functions such that it minimizes the sum of the artificial variables. Right? So let's say, for example, for that particular linear programming, you have three artificial variable, A1, A2, and A3. Right? So what you do, then you need to define a new objective functions. Your objective function is minimize z, where z is equals to a1 plus a2 plus a3. That's what it meant. Set the new objective function such that it minimizes the sum of the artificial variables. So A1, A2, A3 are the artificial variables. So you want to minimize the sum of the artificial variables. So that's the first thing that you need to do. Right? Next, find the basic solution of the resulting equation. So what you need to do, once you define these new artificial variable, new objective functions, which is sum of the artificial variables. Then you use these new objective functions and solve the linear programming problem constraint. So you put the constraint in and you solve an objective function is basically minimize A1 plus A2 plus A3. Right? Next, if once you solved the linear programming using simplex tableau with this new objective functions, if the minimum value of the sum is positive, then the problem has no feasible solution, which ends the process. Otherwise, proceed to phase 2. So once you have, let's say, for example, at the end of the iteration process, at the end of the iteration, they say this is, I don't know, x1, x2, a1, a2, for example, right? And the final solutions that you have is you have x1 and x2, right? So then so x1 has a value, let's say 3, this is 5, right? And this is z, right? So if minimum value of the sum is positive, then the problem has no feasible solution. So for if this is the case, then minimum, then z is equals to, since a1 and a2, sorry, just put a1 and 2, a1 and a2 is not part of the solutions, a1 and a2 equals to 0, then z is equals to 0 plus 0, right? So basically the sum is not positive, is 0 value. Then you proceed to phase number 2. But if let's say, for example, A2 is part of the solution, so X1 and A2 is part of the solution, then basically your Z become 0 plus 5 and equals to 5. So if you solve this, when you have objective functions equal to the summations of the artificial variables, and at the final iteration, optimum iterations, you have z is equals to 5, then the minimum value of the sum is positive. Then if this is the case, then you have to declare that the problem has no feasible solution. End of the process. Right? Any question? Okay. And so that's the phase 1. And phase 2, use the feasible solution from phase 1 as a starting feasible basic solutions to the original problem and solve it using simplex methods. Right? So let's look in detail what that means. Okay. Any questions so far? Okay, so this is the first step. So you convert the linear programming, add all the necessary artificial variables like variables, so on and so forth, right? So this conversion. So you have to do that. That's the first step. Second step, so the first step is put all problem equations form and add the necessary artificial variables, the constraint to get starting feasible basic solution. So you're done this, right? Second, set a new objective function such that it minimizes the sum of the artificial variables. So you create new objective functions. New objective functions minimize R equals to the summations of the artificial variable, which is R1 plus R2, right? The constraint remain the same as before, no change. The only thing that you change is the objective functions. Minimize R equals to R1 plus R2. So you use this and set up the initial table. So if you set up an initial table, this is what it will look like. This is what it will look like. So you have x1, x2, s2, r1, r2, and s3. You have three constraints. So you have 1, 2, 3, r1, r2, and s3, right? And the objective functions, basically, remember the new objective functions for this particular step is minimize r equals to r1 plus r to minimize small r, or whatever you want to use. You can use z, so on and so forth. For this example, use r, right? And basically r minus r1 minus r2 equals to 0. Then in the z or r row, then you have 0x1, 0x2, 0s1, minus 1 r1, minus 1 r2, 0 s3. So this is your initial table. Okay. So there is a problem with this, because if you look at this, R1 and R2 is the basic solution for this table, but the multiplier of the R or Z value here is minus 1 and minus 1. It should be 0, right? So if I substitute this, so R equals to, so R, so R R equals to R1 plus R2. In these solutions, right, R1 is equals to 3, R2 is equals to 6, and R equals to 0, right? So not to get confused, maybe I just put this Z. We are familiar with the Z, right? This is Z, right? This is Z. But then, when I substitute that, then basically R is equals to R1 is equals to 3 plus R2 is equals to 6 and R equals to 9, right? But in this tableau, right, Z supposed to be 0. So there's inconsistency. So we need to address that inconsistency, right? So how to do that? Similar to what we discussed with M methods, we have to make sure that this becomes 0 and this become 0. In order to do that, then basically what you can do is new 0 is equals to R1 times 1 plus R2 times 1 plus the old 0. So, so that's the next step that you need to do. So now we are trying to solve this particular tableau. So we need to address the inconsistency. So again, the old R row is 0, 0, 1, minus 1, minus 1, 0, 0, shown in here. This is the old row. And so rather than M in here, right? So this is supposed to be 1. This is supposed to be 1 because we want to zero it out. So 1 times R, 1 row. So what is so this is R1 row, this is R2 row is 3, 1, 0, 1, 0, 0, and 4, 3, minus 1, 0, 1, 0. So we just copy it, right? And when you add them up, then 3 plus 4 is 7, 1 plus 3 is 4, this is minus 1, 0, 0, 0, and 9. So this will be the new the new R row, and we substitute that into the table earlier table, right? So now the table will looks like this. So no change here, still the same. The only change is this particular new R row, right? And if you want to check this again, we know that R is equals to R1 plus R2, right? This is the objective function. And in this case, R1 is equals to 3, and R2 is equals to 6, and this is equals to 9. So we have a consistent Tableau result in here. Now we can proceed on optimizing this particular initial Tableau using Simplex method. Any question? No? Hmm. Any questions? No? All right.
No.
Okay, so I'm not I think we have done this simplex iteration few times, so I hope that you guys are familiar with it and comfortable with it. So if not, then basically what you can do today, maybe we can end our class today early today. What you want to do, if you have at the end of the class, is actually to work it out. So from here, use simplex method and work it out such that you get an iteration, you get the optimum conditions as shown in here. This is the result. This is final iteration, right? So again, we might be able to finish our, because I'm going to cover until two-phase methods. And I'm going to stop there, and then tomorrow we're going to cover the rest of the chapter. So what I want you to do on the whatever time we have, maybe you're going to have half an hour before 5 p.m. I want you to work it out. So this is initial Tableau. Perform the simplex method using Gauss-Jordan rules, such that the end of it, you're going to you're going to get a final optimized solution looks like this. Okay? So if you didn't get this, meaning there's something wrong with your calculation. Okay? So please attempt that. Okay. Okay. So at the end of it, then this is the final Tableau, and this is basically optimum. Why optimum? Why do I say this is optimum solution? Anybody? Anybody? Why am I saying that this is optimum solution?
Because all the R is a negative value.
Correct. So again, this is minimization. If minimization, you want to know whether it's optimum or not, the multiplier for the R, for the solutions, must be non-positive, right? If one of the multiplier is still positive, then you're in the optimum value. So in this case, we have optimum solution because none of them are positive, right? So once you do that, you do this. At this point, artificial variables have completed their missions, and we can eliminate their column altogether and start phase 2, right? So now once we got this, then we can move to phase 2. right? So so and in phase two, basically, you're going to use this solution, right? But you're going to eliminate the artificial variables column altogether. So this is artificial variables. This is artificial variables. So the next tableau, for the phase two, you eliminate this and use back the original objective functions to solve. Right? So let's look at what it looks like. So now, since so the minimum value of the sum is positive, the process of solution is end, otherwise proceed to phase two. So just now, what we found out that at the end of the iteration process, optimum solutions, then basically you manage to get then the multiplier for R is basically negative value, and the what do you call it? The minimum value of the sum is not positive, is 0. So remember the objective functions for the iterations previously is equals to, sorry, where is it? So the objective functions is basically so the objective function for this is R equals to R1 plus R2, right? So R1, R2 is not part of the solutions. So meaning that this is R equals to 0 plus 0 equals to 0. So R equals to 0. So if the minimum value of the sum is positive, which is not, the problem has no feasible solution with end of the process. Otherwise, proceed to phase two. So since the minimum value of the sum R equals to R1 plus R2 is non-positive, which is 0, then we proceed to phase two. So let's look at what happened in phase two. So in phase two, we're going to use feasible solution from phase two as phase one as a starting feasible basic solution for the original problem, right? So at the end of the iteration of simplex iteration process here, then this is the solution that we got. So what we do is we copy this particular result for phase two. And this is basically what that result is. Right? This is what that result is. The only thing we do is basically we're going to eliminate the artificial variable column. We're going to take it out. And now the tableau become this. So you have x1 equals to 1, 0, 0. So 1, 0, sorry, 1, 0, 1 over 5, 0, 1, 0, 1 over 5, 0. 0, 1 minus 3 over 5, 0. And S3 is 0, 0, 1, 1, 0, 0, 1, 1. The Z row in here, then use back the initial original problem where we have minimized Z equals to 4x plus x2, 4x1 plus x2. So then this become Z minus 4x1 minus x2 equals to 0. So in the Z row, then you have Z minus 4x1 minus 1 x2. There's no s1, and S2, S2 and S3 is 0, 0, and the solution is 0. Right? Okay. And the initial solution is similar to the initial solutions of the first phase, which is x1, x2, and S3. Remember that? And z value is equals to 0. Okay, so then when we look at this, then we know there's issue with this, because if you look at the basic solution is x1, x2, S3. So this is x1, x2, and S3. So the multiplier of z for x1 is -4. This should be 0. For x2 is -1. This should be 0, and this is okay. So because of that, we have to fix this inconsistency, because if I plug in this value to the objective functions, so z equals to 4x1 plus x2. If I substitute x1 equals to 3 over 5 and x2 equals to 6 over 5 into the original objective functions, then if you calculate, what you get is 18 over 5. However, in the tableau is 0, so there's inconsistency. So because of that, we have to correct this inconsistency using this equation. Now, new row, new z row is all 0 plus 4r1 row plus 1r2 row. Why 4r1 row? Because we want to eliminate this -4. So because of that, we have to times 4 in here. So become 4, 0, 4 over 5, and then 12 over 5. And x1 here, we want to eliminate this -1, so we times 1 in here. Okay? That's one. Okay? And if you perform that, then we're going to get a new z row. If you look at this, the old 0 is this, -4, -1, 0, 0, 0. 4 times R1, so this is R1. So if 4 times R1 become 4, 0, 4 over 5, 0, and 12 over 5. And similarly, we want to eliminate this by multiplying 1 times R2 row. It become 0, 1 minus 3 over 5, 0, 0, 5. When you add them up, -4 plus 4 is equal to 0. -1 plus 1 equals to 0. And 4 over 5 plus minus 3 over 5 equals to 1 over 5, 0. And you have 12 over 5 plus 6 over 5 become 18 over 5. So this is your new 0. And you substitute this new 0 into the initial tableau. Right? So it's the same process as we discussed for the big M and the first phase just now. Okay? So now, so when you replace this, new 0 in here, then this become your initial tableau. This become your initial tableau. And you can start the simplex algorithm on this. Okay. So if you do a simplex algorithm, now you apply the simplex methods as before. Since this is again minimization problem, we select the entering variables with the most positive objective functions row, most positive objective function row coefficient. And in this case, the only positive is basically 1 over 5. Right? So this will be entering. Which one will be leaving? Then basically, this will be your pivot. So then you divide this 3 over 5 divided by 5. So this become 3. 6/5 divided by, this is negative number. You can ignore it. 1 divided by 1 is equals to 1. So you know that the next table, basically, S1 will be entering and S3 will be leaving. So your next tableau will be X1, X2, and S1. And then you perform the simplex methods as we did before. Right? And if you do that, basically, after one iteration, uh, uh, you're going to continue, you're going to achieve the optimum solutions. And the optimum solution is X1 equals to 2/5, X2 is 5/9, S2 is equals to 1, and Z equals to 15/5. So this is basically same result that we got, same with big M method. Okay. Right. So this is a two-phase methods, and most of the software is using this method to solve linear programming problem, simplex linear programming problem. Okay. Any questions?
No, Doctor.
So some remark. Um, the removal of artificial variables and their column at end of phase 1 can take place only when they are all non-basic. Right? If one or more artificial variables are basic at 0 level at the end of phase 1, then the following additional step must be undertaken to remove them prior to start of phase 2. So remember, let's say at the end of phase 1, so I'm simplifying this. Okay. Let's say you have two artificial variables. So you have x1, x2, a1, and a2. Right? And then your final solution is x1 and a1. Right? X1 is 5. Right? So the removal of artificial variables and their column at end of phase 1 can only take place when they are all non-basic. Right? If one or more artificial variables are basic at 0 level, meaning that A1 is one of the solution, but its value is 0. Right? At the end of the iterations, A1 is still part of the basic solutions, so it's still in the basic solution variables, but its value is 0. If the value is non-zero, then you stop. But if the value is 0, then if one of the artificial variable are basic at 0 level at the end of the phase 1, then the following additional step must be undertaken to remove them prior to the start of phase 2. So you need to proceed. You cannot just stop. You need to proceed. But you need to remove this. How to do this? This. Step 1, select 0 artificial variables to leave the basic solution. Choosing the living variables and designate each row as a pivot row and the entering variables can be of any non-basic variable with non-zero positive or negative coefficient in the pivot row. So this is what it meant. Right? So let's say, for example, you're having this particular condition. right? Where A1 is part of the basic variables, but its value is 0, right? So now you need to remove this A1 from the basic solutions. How to do it? Select 0 artificial variables to leave the basic solutions, meaning that this going to be living. No matter what, I'm going to take it out from the system, right? And designate its row as a pivot row. And you designate this particular row as a pivot row. Right? The entering variables can be any non-basic variables. So in this particular case, x1 is here. The only non-basic variables in here is x2. And this non-basic variable with a non-zero, doesn't matter positive or negative, coefficients in the pivot row. So in the pivot row, this x must have a value. Doesn't matter whether it's positive or negative, right? So it can be -1 or +1, doesn't matter, as long as it's not 0. If this is 0, then you have to choose other non-basic variables, if any, right? So that's what it meant. The entering variables can be any of the non-basic variables with non-zero, positive, negative coefficient in pivot row. Perform the associated simplex iteration. So basically, what you're going to do, this is going to be leaving, this will be entering, right? And then basically you change these value by the same Gauss-Jordan rules, meaning that you divide all this multiplier with that pivot number, right? And then you change x1 value with a Gauss-Jordan rule also. Okay. Step 2, remove the column of the just leaving artificial variable from the table. If all the 0 artificial variables have been removed, go to phase 2. Otherwise, go back to step 1. Okay. So once you do that, then basically you need remove the column of the just leaving artificial variables, meaning that for this one A1, you remove this particular column, right? So A1 is no longer there. If all the 0 artificial variables has been removed, go to phase number 1. So if you do that, then basically if the iteration process, right? A2 is not the if A2 is not the new entering variables, then basically you are done with it. Okay. Otherwise, go back to step number 2 and you repeat the whole process again. Right? So this is applicable whenever at the end of the phase 1, you have artificial variables as part of the basic solutions, but its value is equal to 0. If you do that, then basically what you need to do is force it out. How to force it out? Then you select the entering variables and A1 will be the leaving variables, and remove the A1 column, right? And then once you do that, then you calculate the z value, so on and so forth, see whether there is still optimum, whether the solution is optimum or not. If it's optimum, then you're okay. If it's not optimum and you have to replace A1, A2 as part of the basic variables, then basically you need to repeat the whole process again. That's what it says in here. Okay. Any question?
No, Doctor.
Okay. So that's basically the end of the two-phase methods. So you have about 1 hour left. this particular class. So what I want all of you to do after this, we're going to sign off. But within this 1 hour, what I want you to do is to practice. Practice what? On this, on the two-phase method. The first one is basically hold on. Use this as a initial use. Oh, sorry. So use this tableau as the initial solution, right? And then perform simplex methods using Gauss-Jordan, right? Such that you get the result, and your result should be this. This is the optimum. If you didn't get it, maybe something wrong with your calculations, and you have to check, make sure that you solve it. If you have issues, then you can contact me or ask your friends or whatever. Right? Once you got this, then basically the next step is basically I want you to again use this as the starting solution. Okay, and again perform simplex methods. Okay, and you should get this as a result. If you didn't get this as a result, then something wrong with your calculations. So I want you to have some practice on doing this. Eh? Would that be okay?
Okay, Doctor.
Okay. So basically that's what I want to do for the next 1 hour. Some exercise, and then tomorrow we're going to finish up our lecture, and tomorrow we're going to look at the sensitivity analysis. What we need to do there is basically we're going to look at again the solver, Excel solver, and use Excel solver to solve certain problem and come up with a sensitivity report, and how to interpret sensitivity report and what it meant. And basically if we have time, then we're going to go through another topic on what's another topic. I forgot what's another topic. There's now one more topic, and we should wrap up our class by then. So any questions before we sign off, and you guys go ahead and do some calculations to solve what I asked you to do just now. Any last questions from any of you? Boleh?
No, Doctor. Okay.
All right. And again, you can start attempt on the assignment and also case study. I think assignment 1, you can start doing it already. On assignment 2, it required some discussion on sensitivity report. So tomorrow we're going to cover that. All right. So if there's no questions, then basically I'm going to let you guys go and go ahead with practicing on the exercise I mentioned just now. And I'll see you guys tomorrow. Right?
Okay, Doctor. Thank you.
Okay. If no question, then thank you very much. Assalamualaikum. So you can ask questions with regards to what we discussed just now in the WhatsApp group, or you can personally message me. Right? Thank you.
Okay.
So,
Thank you, Doctor.
Thank you, Doctor.
thank you.
Thank
Bye-bye.
you. Assalamualaikum.
Salam.
Thank you, Doctor. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Stop recording.